We'll just give it one more minute for everyone to join the Zoom call, and then we'll get started. Okay, uh, we're above 1,000, so let's get started. Hi, everyone. I hope you've had a really, really wonderful week. Hopefully, you're having a great time in your labs, and great to see you back here for lecture. Just one really quick announcement for me. Next week before lecture, so in that same time frame that we tend to have special events from 1 p.m. to 1:45 p.m. Eastern time, about an hour before lecture, we're going to do a panel discussion with some of the teaching assistants and instructors about like academic opportunities and careers in quantum computing. So we've heard so many questions from students about, should I take this class or this class? What's the right degree program to pursue in undergrad? How do you get a job in quantum computing? And so there's no one answer, and we want you to hear from the TA directly about what it's been like for them navigating this really new space that is quantum computing. So we'll post more information and the links on Canvas this week, but we hope to see many of you there for what I think will be a really interesting and helpful discussion. Other than that, just continue to check the announcements on Canvas. A reminder that we have office hours if you need assistance with your homework. We have Piazza where the TAs can answer your questions, and lots of resources available if you're struggling or if you just want to ask additional questions about what you're learning in lecture. So with that, I will toss it to Amir, and you can take us away with what, the third of 3 quantum mechanics lectures.
Third one indeed. Thanks, Rachel. Hi, everyone. Welcome to another lecture. Today, we're going to be talking about postulates of quantum mechanics. But before we dive in, let's do a quick recap of what has been done in the past, what we've seen in the past 2 quantum mechanics lectures. So in the first lecture, we talked about the principles of quantum mechanics, specifically what is quantum actually, and how do things behave in the quantum length scale, which is, again, if you remember, the scale and the regime where our qubits are operating, or quantum bits are operating for quantum computing. In the second lecture, we talked about quantum two-level systems and measurement, and specifically, what are two-level systems and what can we do with them. So a quantum bit is a quantum two-level system because when you measure it, or rather it can have 2 possible values, 0 or 1, and it can be in a superposition of 0 and 1. So the 2 levels are 0 and 1, and everything that we do, all the qubit operations are acting on these 2-level systems. And some cool properties that we've discussed in the past 2 lectures are superposition, quantum interference, which again comes from wave-particle duality of quantum objects, or really any object, but specifically at the quantum level, that becomes very obvious. And we also talked about quantum entanglement, which is a strong correlation, a strong beyond classical correlation between quantum objects. Now, these 3 resources are necessary to get a quantum speedup, but of course, they're not always sufficient. And that's an active area of research as is. But today, we're going to talk about, again, the postulates of quantum mechanics, and really the objective that we're trying to focus on, and what are the foundational rules for quantum mechanics. And again, we've seen a lot of these throughout the past semester and these couple of past lectures, but now we're just putting them in a formal set of rules that then we can take with us to quantum computing and build on top of them. So again, today we talk about the 6 postulates of quantum mechanics. The first postulate describes a quantum state. Again, I think by this point we have a good idea of what a quantum state roughly is, but we're going to talk about that in more detail. Postulates 2 and 3 focus on observing and measuring the quantum state. So what happens when I make a measurement? Or rather, I guess what happens, like, what can I measure rather? And postulates 4 and 5 focus on what happens after a measurement. So after we collapse a superposition. And finally, the 6th postulate talks about how does a quantum state change with time. And if you remember from the first lecture in the sequence, something that describes an equation that describes how quantum states evolve in time is a Schrodinger equation. And the Schrodinger equation is actually a result of the sixth postulate, which is a very neat derivation that we're not going to go into, but I would highly recommend you guys look into if you're interested. And of course, we're going to cap the lecture by talking about how do these postulates relate to quantum computing. Okay, with that, so let's look at this amazing graphic that kind of should give you guys a rough idea of, like, what do we mean? What are the postulates of quantum mechanics? So postulate means an assumption used as a basis for mathematical reasoning. So in a sense, if we think of the things that we discuss in this class as a house, again, quantum mechanics, quantum information, quantum computation, and research, the postulates are the foundations on which this house is built. So again, there's a set of assumptions that we make about quantum mechanics, and then everything else, in a sense, follows from these assumptions. Everything else you can derive after you start with these assumptions. So with that, let's dive right in. So the first postulate states that a quantum state is represented by a ket, and the ket is here, of course, psi, in the state space. So what does this really mean? Let's think of a classical analogy first. So if I'm running, you can create a function that describes my path on a coordinate system. So that is the physical image that I want you guys to have in mind when you're thinking about the first postulate. And again, one important consequence of the first postulate is that the superposition of any two quantum states is also a quantum state. So I can have a state psi, quantum state psi, equal to, yes.
Can you just slow down a little bit?
Sure.
Cool.
Okay. So, yeah. So, okay. Again, we're gonna actually take our time with going through the postulate. So, if that was a little too fast, I apologize. But we'll see them. So, if I have two quantum states, let's say maybe quantum states psi1 and psi2, I can create a superposition of the two. So let's say the state psi is A1 times the state psi1, and we're assuming psi1 is a quantum state, plus A2 times psi2. And psi2 is also a quantum state. Now, the one condition that we have to satisfy here, again, similar to what we've seen in the past, assuming that psi1 is normal, because it's a quantum state. So the overlap of psi1 with psi1 has to be equal to 1, and the overlap of psi2 with psi2 also needs to be 1. So that being said, this A1 and A2 can be are complex, similar to what we've seen already with any quantum state. And again, we're going to go through an example to make this a little bit more concrete. And A1 magnitude squared plus A2 magnitude squared is equal to 1. So let's look at an example. So I can have some state psi equal to 1 divided by square root of 2 times the 0 state plus 1 divided by square root of 2 times the 1 state, right? So again, here 0 and 1 are quantum states, and they check these conditions, and I can put them in a superposition and make another quantum state. Again, as long as I get these probability amplitudes right. Okay, let's look at another case. So let's say I have a psi1 that is equal to, actually, the psi that I have up here. So this is example 1, and this is example 2. So I have a psi1 that's equal to 0 plus 1 divided by square root of 2, and a psi2 that is equal to the 0 state. Say. And I want to create a superposition of this too. So let's say I have psi, this other quantum state that I'm creating that is equal to, again, got to get the normalizations right. 1 divided by square root of 2 times psi1. So, okay, let me add commas here. Plus 1 divided by square root of 2 times psi 2. Right? So now let's think about this. I'll let you guys think about this for 30 seconds before I do it myself. But so based on the definition that we have for psi 1 here and psi 2, what is the psi equal to? Yeah, take 30 seconds, try to do it yourself, and then we're going to go through it together. Okay, so yeah, let's do this together. So here I'm going to plug in whatever, whatever definition I have for psi 1 and whatever definition I have for psi 2. So oops, zoom in. I have 1 divided by square root of 2 times 0 plus 1 divided by square root of 2, and then plus 1 divided by square root of 2 times, and this is just a 0 state. And actually, one thing that I'm going to notice is that this is going to be equal to, so I have 1/2 plus 1 divided by square root of 2 in front of 0 plus 1/2 times the 1 state. Actually, maybe let me go back. I didn't want to show that quite yet. And something that you will notice, and you can try this on your own, is that if I take whatever probability amplitude is in front of 0, square it, and then add it to the probability amplitude in front of 1, I'm going to end up with 1 again. The overall state is going to be normalized. Okay, and again, with that, the classical analogy that I can give you for this, the consequence of the first postulate is that no matter what path I take while running, you can always represent my location as a point on the coordinate system. And in fact, this quantum coordinate system is called the Hilbert space. Yeah, Hilbert space is a word that you might see around if you dig into the literature of quantum computing or quantum mechanics for that matter. And what it really means is a space in which all the quantum systems exist. In other words, you can think of it again as a coordinate system that can describe any quantum state, similar to how a normal coordinate system can describe the location of a runner. Okay, with that, I'm going to move on to the next postulate now. So the second postulate talks about how classical observables are introduced into quantum mechanics using operators. So far, this part indicates how we can kind of take things that we see in the world around us and fit them into quantum mechanics. Specifically, every observable, which is what an observable means, is a measurable property. And again, we're going to see some examples of measurable properties on the next slide. But any observable of a physical system is described by an operator that acts on the state, ket. So, one classical analogy that I can offer for this is, again, if I'm running, right, in the classical world, you can kind of tell me what my speed is. If you have a speedometer, you can tell me which direction I'm heading. You can kind of see my position. If you have some fancy way to measure the energy, you can measure how much energy I have while running, what is my momentum, and all those properties. These are observable properties, again, in the classical world. Now, again, classically, we can find these values by measuring them. For example, we can measure the energy of something, and you can tell me what the energy is. Now, in quantum mechanics, we use an operator to the wave function or the quantum state, which is the ket, to get these values. For example, kinetic energy is going to be equal to the kinetic energy operator acting on state psi. Or rather, the operator is something that gives us the value of, or that the property that we're looking for of a specific quantum state. And I really like this graphic here because I think it really completes the picture. So again, you have an operator that acts on a wave function, or again, a quantum state. And if it's a momentum operator, it tells you what the momentum of that wave function or that quantum state is. Or for example, if you have an energy operator acting on, again, a wave function or a quantum state, it tells you what the energy of that quantum state is. So that is what an operator is essentially. Again, we've discussed this in the past, but it's good to revisit it. And so the consequence of the second postulate is that it relates to observables that we can measure. Again, things that we can see in the world around us, or properties of a quantum system that we can measure to the quantum world. So in a sense, it's linking the classical world around us to quantum mechanics and the quantum world. And again, for every operator, so let's look at a couple of these examples. So going back to the Stern-Gerlach case, for example, we can measure spin. Can measure the spin in the z-axis, or along z, let's say. Using the Pauli z operator, which we're going to show as sigma z, or just capital Z. And both of these are common ways of showing it in the literature. And just as a reminder, the matrix associated with this operator is going to be 1, 0, 0, and minus 1. Or similar things. So we can also measure the spin along the x-axis this time, using, if you had to guess, you probably would guess Pauli x, and you'd be correct, which again, we can show us something that's capital X. And the operator, the matrix for this operator looks like 0, 1, 1. And so on and so forth. So again, this operator, this postulate, I think, does a good job of relating the observables that we saw with the Stern-Gerlach experiment to actual quantum mechanical operators that we can then use to calculate or predict what will happen. Yeah, we're going to elaborate on this with the next postulate. But again, the idea of the second postulate is that when we measure something, we can kind of relate that measurement to a quantum operator. Now, there's one thing that needs to be special about this quantum operator, right? So again, if you guys remember from the previous lecture, and we've also discussed this throughout the past couple, the previous semester, and we've also discussed this throughout the past couple of lectures, is that measurable operators have to be Hermitian. And what Hermitian means, again, for review, is that if I have operator A, then A has to be equal to A dagger, or its own complex conjugate. And of course, there are some properties of this Hermitian operator that we're going to talk about again on the next postulate. But this is actually very important. So again, this is why we talked about Hermitian operators when we're introducing quantum operators in the first semester, because Hermitian operators are the operators that we can actually measure and to get a result in real world. So just going back to a previous slide here. So all these properties, all these measurable properties that we talked about, when we are translating them to a quantum operator, they need to be a Hermitian quantum operator. Now, the energy, the operator for energy is a Hamiltonian, if you remember from previous lecture, or actually, sorry, not the first lecture of the sequence. And the Hamiltonian is Hermitian. The operator for momentum also needs to be Hermitian. And the operator for position also needs to be Hermitian, because these are all properties that we can measure. Now, the third postulate states that the result of a measurement of an observable with an operator A will only ever be an eigenvalue of A. So let's talk about a classical analogy, then we'll review what eigenvalues and eigenvectors are, and then we're going to talk about the consequences of this postulate. But the idea here is that we don't have a real life example. Actually, it's kind of difficult to think about in terms of a real life example because this is explicitly a quantum concept. The speed of a runner can only take certain values. So again, if you think back to the analogy that we had with steps and the slide, in the classical world, things can be continuous, or rather we perceive different things to be continuous. Whereas in the quantum world, of course, there are, things tend to be discrete. Actually, this discreteness comes from the fact that if we have an observable operator, there are only certain eigenvalues that we can have. So once we measure the value of something, the value of a quantum state, that potentially an eigenstate, there are only certain possible values that we can get. So let's review what we mean by eigenvalues, and then we'll discuss this postulate a little bit further. So if I have an operator A, this is my operator A, and let's put a hat on top of it. V will be an eigenvector or an eigenstate, I'm going to call it, of this operator A if and only if, when I apply A to this vector V, I get the same vector V on the other side times a constant. And this constant is lambda, and we call the constant eigen value, or sometimes eigenenergy, but let's just stick with eigenvalue for now. And in German, eigen means proper, characteristic, or own. So again, the idea here is that if I have an operator and I apply it to some specific vectors, I get the same vector out on the other side times a constant, or a scalar, which is the eigenvalue. And now the consequence of this third postulate is that it allows us to determine the possible outcomes of an observable measurement. So maybe actually, again, let's apply this to what we've talked about with the CERN-Gerlach experiment. So if I'm measuring along sigma z, so the example here is, of course, measuring along the z-axis for the SG CERN-Gerlach experiment. So the eigenvalues of sigma z, or eigenvectors rather, the eigenvectors are, actually I should do, maybe let me erase this real quick to make it a little bit neater. The eigenvectors or eigenstates for sigma z are, so I'm going to call this in a very suggestive way, 0, which is the 1, 0 state, and 1, which is the 0, 1 vector. And this is something that we can quickly check. And again, as a reminder, sigma z, of course, is a matrix that is 1, 0, 0, minus 1. So if I apply sigma z to the 0 state, I get plus 1, and again, this is just 1 times the 0 state, and if I apply sigma z to the 1 state, I get minus 1 times the 1 state. So here 0 and 1 are the eigenstates or eigenvectors of the sigma z operator, and the plus 1 and minus 1 are the corresponding eigenvalues. But now the idea is that if I measure along the z-axis for the CERN-Gerlach experiment, the possible outcomes will be either the 0 state, which I'm showing with this vector, or the 1 state. And again, the 0 and 1 are the eigenstates of the sigma z operator. Now let's look at another example, and I want you guys to take some time thinking about this. Maybe take a minute before we go through it. So again, revisiting the Stern-Gerlach experiment, what happens if I measure along the x-axis instead? And again, something that we discussed in a couple of previous slides or earlier was that the operator associated with measuring along the sigma x-axis is this, well, okay, not sigma x-axis, but just the x-axis is this Pauli x operator, which is 0, 1, 1, 0. So yeah, maybe let's take a minute and think about what the eigenvectors are for sigma x. And again, this is something that we've seen before. So if you have to go through your notes and revisit this, that's totally fine. Because we're just repeating this now in terms of a formalized postulate instead of talking about a specific experiment. But yeah, think about what the eigenvectors are, and then based on that, we can discuss what the possible outcomes are. So again, take a minute, think about this, and then we'll go through it together. Okay, so again, let's look at this together. And this time I'm going to write eigenstates in terms of eigenvectors, just to tell you guys that they're the same. So the eigenstates, and again, I'm going to make a sign here that says same thing, maybe. The eigenstates of sigma x are, again, I'm going to refer to this as a plus state. We've seen this many times. It's 1 divided by square root of 2 times 1, 1. And the other eigenstate is the minus state, which is 1 divided by square root of 2 times 1 minus 1. Now, if I apply this Pauli x operator to the plus state, I end up with, again, plus 1 times the plus state. If I apply this Pauli x to the minus state, again, as defined over here, I end up with minus 1 times the minus state. And actually, in fact, the eigenvalues are the eigenvalues of Pauli x operator are why we call them the plus state or the minus state commonly in the literature. So based on this, the possible outcomes of measuring the spin of the Stern-Gerlach, for example, experiment along the x-axis are this plus state and the minus state. Again, this is something that we've seen in the previous lecture. Now, what we're doing now in the form of the third postulate is that we're formalizing it such that it extends to beyond just the Stern-Gerlach experiment. This is in fact something that you can take from the third postulate and directly use it when it comes to quantum computing. So with that, I think Rachel, you have a few questions for me. So let's take some time to go through those.
Yeah, I think it's a lot of new information. So let's just kind of break some things down and review you introduced. So the most basic question, remind us, what is a postulate? It's kind of a funny word. What does that actually mean for quantum mechanics?
Yeah, and again, I love this kind of slide that Sarah actually made for us. So a postulate is an assumption that is used as a basis for mathematical reasoning. And a good way that I like to think about it, and again, it's kind of obvious um, in this graphic, is that the postulates of quantum mechanics are the foundations that everything else is built on top of. So, for example, the way that we link the quantum to the classical world, that is a basic assumption, and then based on that, we can decide, figure out what happens at the end of our quantum algorithm once we measure, once we have this quantum circuit, and then we want to actually see the values in the classical world. So again, there are these underlying foundational assumptions that essentially the rest of quantum mechanics is built on top of, with mathematical reasoning and lots of linear algebra.
So maybe to take that a step further, what's kind of the history behind the postulates? Were these discovered through experiments?
Mhm.
Like, how can we safely make these assumptions?
Yeah, actually, that's a great question, and there is a good bit of history behind these postulates of quantum mechanics. Because when people were developing quantum mechanics, I mean, obviously, no one had an idea what was happening. There were weird things happening, or at least what people perceived, scientists, physicists perceived as weird things happening that they couldn't explain with the classical theories that they had. And most of these postulates actually come from Schrodinger, specifically, these not Schrodinger, sorry, Heisenberg, specifically, the postulates that relate quantum states to, again, or, measurement, or rather map, or like describe measurements with the in the context of quantum mechanics. So what Heisenberg specifically emphasized when he was developing his version of quantum mechanics, which is the matrix mechanics that we commonly use in quantum computing, was that in quantum mechanics, or for quantum physics, we only care about things that we can measure. Yeah, things that we can actually experimentally see around us in the world. And then he started from that assumption, which again is a lot of these postulates, and derived the rest of quantum mechanics with linear algebra. So he asserted that the operators, like again, the operators that we can measure need to have these properties. Again, they need to be Hermitian. We talked about it. Everything that we can measure has an operator associated with it, and worked kind of like work backwards from these set of assumptions to get everything else. So in a sense, these postulates are assumptions that we need to make, and everything else is kind of built on top of this foundation. And again, to emphasize, these postulates, of course, are not just someone's like random theory. They're rooted in reasoning and in, again, mapping the physics that we see around us in the classical world to the physics that was being discovered. And in fact, quantum mechanics is one of the most successful theories in human history. It's it's like stood the test of time for well, over almost 100 years now, a little over 100 years now. And again, it's all built on top of these set of assumptions. So since a theory is so successful, it's very clear that these postulates are also very powerful in a sense.
Cool. Okay. So now that we understand what they are, why they're so important, can you just bring us through the three that you've introduced at a very high level and recap what like kind of the key takeaway of each?
Yeah, that's great. So let's talk about the first postulate again. It says that a quantum state is represented by some ket in state space. And I think the key here is the state space, which we also refer to, again, let me be write it here, as Hilbert space, for the fancy term. And really, what the important thing about this postulate is that if I have two quantum states, I can construct another quantum state that is a superposition of these two quantum states. So, for example, the plus state, or this 1 divided by square root of 2 times the 0 state plus 1 divided by square root of 2 times the 1 state, is a superposition of two valid quantum states. So 0 and 1, rather the 0 state and the 1 state are each a valid quantum state. And I can kind of mix and match them to create a superposition state. Now, this only doesn't, this postulate kind of extends beyond just the 0 and 1 state, right? So the next example that we talked about is if I have, this superposition state, I can also create a superposition of that with a 0 state. And again, it's as simple as just making sure that the coefficients that we have in front of these valid quantum states, essentially when we square them, they add up to 1. Again, the takeaway message here, if the math doesn't make any sense to you, which hopefully by this point it should, is that the superposition of any two quantum states is also a quantum state. That's all there is to it. Now, the second postulate, this is a little bit wordy, but really the real consequence of the second postulate is that it relates, observables that we can measure, things that we can see around us in the world, to the quantum world. So in a sense, it's a bridge between the classical world and quantum physics. And this is what I meant. So this is actually like one of the cornerstones of Heisenberg's assumptions when he was creating his version of quantum mechanics. And again, these postulates, all these postulates are actually, and they're so successful that this version of quantum mechanics is very powerful in predicting many things that we see around us in the world. Well, not the classical world, but in experiments in the quantum world. And they've been tested over and over and over and over again for hundreds of years. And now that we have quantum computers, of course, there are going to be even more experiments done. And, they work. So it's a beautiful theory. So the third postulate says that the result of a measurement of an observable with an operator, some operator A, which has to be Hermitian. Again, we've talked about the definition of Hermitian, will only be an eigenvalue of A. And really what the consequence of that is that, it tells us what the possible outcomes of an observable measurement are. And for a lot of the operators that we see around us in the world, there are a finite number of eigenvalues, which means that, when you measure, you can only get, a certain set of possible values as outcome. So now this draws a stark contrast with what we're used to seeing in our classical world. Because in the world that we see around us, in a sense, we're used to things being continuous. Again, at least at the scales that we can see, that we have some intuition for. But now in quantum mechanics, of course, and again, this is something that we've discussed in the previous two lectures, is that things tend to be discrete. And this discreteness is a consequence of the third postulate, which again, since the things that we can only measure can be selected from a finite number of values and nothing in between, that's where the discreteness comes from. So that is the significance of this third postulate, in a sense. And that was it's at least for what we've seen so far. There are 3 more coming.
Okay, so on the third postulate, if students think back to last lecture, the picture side by side with the slide versus the stairs, right? That's the point of this one here.
Yeah.
Cool.
Exactly, and I kind of wish we'd added that here, but I guess we have the ladder at least, so you can think of it again as a ladder versus a runner. So when you're climbing a ladder, you can only step on kind of discrete heights from the ground wherever there's a ladder step. Whereas when you're running, at least for a classical observable, you can be kind of between any two positions.
One more question I want to ask, because it's come up in a few contexts. So when we're talking about eigenvalues, what are the sphere of, like, that they can be a particular value? Is it just +1, -1, or like what determines the scope of what is an acceptable eigenvalue?
That's a great question, and I guess so that is something that we could have discussed in the for the context of the third postulate, and maybe I will talk about it a little bit more after the break. I'll add an extra slide and we can talk about it. But in general, it depends on the operator, what the eigenvalues are. Now, for the Hermitian operators that we talked about, these special operators that we can measure, what is special about these eigenvalues is that they have to be real. And just taking the math out of it, from an intuitive perspective, that should make some sense to you because of the things, the values that we can see around us in the world are all real values. I mean, in fact, when you learn imaginary or complex values, it's something that initially might sound mathy and abstract. And the reason for that is because you don't see them around you on a daily basis. So I think this is actually another neat consequence of the fact that why the observables that we can measure have to be represented um, by Hermitian operators because again the stuff that we see around us in the world, the things that we can measure, are all real. Complex numbers are not something, the position of something can't be complex. It's a real number. So I think, and that's a neat thing. And maybe we're going to go on a break after this, and then I'll add a slide after this third postulate slide, and before we dive into more questions.
Cool. Then maybe one last question I want to try to sneak in to make this even more
no
concrete.
Break yet.
Sorry. Amir, can you try to say anything about how the three postulates we've gone through so far are relevant to either your research or some of the important questions in quantum computing? Like, do these allow us to make assumptions that skip steps in research? Yeah, that kind of thing.
Yeah, so we'll talk about this, of course, at the end when we've introduced all the postulates. But so far, what I can say is that the first, like at least postulates 2 and 3, are very important when it comes to quantum computing because they essentially tell us what happens when we measure our quantum circuit at the end of our quantum algorithm. And again, there's kind of the fourth postulate that also explains it a little bit more. But in general, the end of any quantum algorithm in quantum computing is measurement. When we take the quantum state and we somehow look at it and kind of translate it to the classical world, measurement. And postulates 2 and 3 at least, and 4 again, which we will see, tells us what happens after we measure our quantum circuit. So that's the relevant to like quantum computing. But again, I feel like once we see all 6, we can kind of talk about that more because some parts are related to each other.
Cool. Let's jump to break if you're ready for it.
Yes. Okay, so let's take a break till 2. Okay, we're 10 minutes, 2:54 Eastern time, but different for different people.
I just dropped an article in the chat too. There's a great story out of MIT News about Will Oliver. So if folks are looking for reading over break, Will Oliver's on our board for Qubit by Qubit. So you might enjoy that. Cool.
Okay, everyone, let's begin the second half of the lecture now. So before I move on, maybe let's go back and talk about the Hermitian matrices and operators a little bit more. So maybe I'll do a quick recap of these vocab words after the break slide. But for now, what I mentioned earlier is that uh, all. Maybe let me change this color because I know some of you guys don't like it. So what we talked about is that all measurable operators are Hermitian. And what Hermitian means again is that if I have operator A, then A would be equal to its own adjoint. And now a consequence of that is that all eigenvalues of Hermitian operators are real. And again, as we discussed before the break, this should make some intuitive sense because the things that we see around us in the world are real values after all. Now, we're going to talk about what happens after we make a measurement. But let's say I have an eigenstate or an eigenvector for this operator A, such that when I apply A to this quantum state, let's say small ai, I get the value ai out times, again, the state ai. So again, just to recap, this is the eigenvalue, the coefficient in front, and then these are the eigenstates of the A operator. So based on this, again, since A is Hermitian, all of these possible eigenvalues, again, all AIs, will be real. So now you might ask me, what happens, when I make a measurement? Well, we're going to talk about that when we get to the next two postulates. But, you can think of the expected value of a measurement, the value that you will get out if you measure something, as in this case, it's going to be bra AI, and then we're going to have this A operator sandwiched between the bra AI and ket AI. So again, let's look at the example that we have up there. So when I act, so I can act with this operator on this ket, right? So when I act on that operator with the ket, what I end up with is just the eigenvalue times the eigenstate. So I will end up with, and then let me write this. So I will end up with state or ket AI, the eigenvalue AI, and then the state AI. And since this is a constant, this AI that I have here is just a constant, it's an eigenvalue, I can move it out here. So I will end up with AI and then the overlap of AI with AI. Like the overlap of the state AI with itself. And this will just give me AI because we know that this is one. So yeah, that is what happens. That's the expected value that I get when I measure an operator on a quantum state. This is the expected value for measuring, if I have the quantum state, AI, the ket AI, and I measure the operator A on this state, the expected value that I get is the eigenvalue. So this is compatible with what we told you earlier. And now let's talk about these eigenstates of Hermitian operators for a moment. So, okay, what I said is that, okay, all the eigenvalues have to be real. But now what about the eigenstates?
Amir, could I ask a quick question?
Yes, yes.
So when you write the eigenvector as get AI and the eigenvalue as AI, are you saying that the eigenvector is the same as the eigenvalue?
Well, so the eigenvector is this is actually a common way of representing this, and I understand how it could be confusing. So the eigenvector, can think of it as a vector, right? At the end of the day, if it's a qubit, it could be a column vector with two entries. It could be larger and larger. But this AI, so the AI that I have in the ket, this is a quantum state, or a vector, if you like to think of it that way. And now this AI that I don't have in a ket is just the eigenvalue. And this is common notation that you will see in quantum computing and quantum mechanics literature. And you just have to be a little bit careful. So I think that was a great question, Akshay. Are there any follow-ups to that?
No.
Okay, amazing. Now, what is special? So, okay, so these Hermitian operators. What I told you is that, since A is Hermitian, all of these eigenvalues, and maybe let me add that here, all eigenvalues will be real. And now, as for the eigenstates, if I look at the overlap of, maybe let me, oops, sorry, let me erase that. Eigenstates. So if I'm taking the overlap of an eigenstate with itself, let's say, AI with AI, then this will be equal to 1 because all eigenstates are valid quantum states. But now if I take the overlap of AI with AJ such that, I is not equal to J, then, this overlap will be 0. Or they would be orthogonal. Another way of showing this is, that AI, AJ, is equal to this Kronecker delta, IJ, which what it really means is, 1 if I is equal to J, and 0 if I is not equal to J. And actually, maybe that's getting a little crowded there. So, again, AI, AJ, for arbitrary indices I and J would be equal to this Kronecker delta IJ, which would give me 1 if I is equal to J, and 0 if I is not equal to J. Again, if you guys remember, this property has a name that we talked about in previous lectures, and that's called being orthonormal. So a quantum state, so in this case, the eigenstates are orthogonal, orthogonal with the different eigenstates, and they're normal, meaning that their overlap with themselves is 1. Again, if that's too much math, don't worry about it too much. Again, this is something that we will see more concrete ways when we get to quantum computing. The important takeaway message here is that again, all measurable operators have to be Hermitian. And one of the properties of the Hermitian operators are that the eigenvalues are real. So meaning that when we measure something in the quantum world, we need to get a real value out in the classical world, not something that's complex, for example. Okay, with that, let me go to the next slide. Okay, so this is what we're supposed to do before the break. And now let's review a few vocab words, and I think they gave me a list, so I will go through those. Okay, so yeah, operator. So we've been talking about quantum operators, right? Yeah, all quantum gates are quantum operators, and the general definition is that they map a quantum state to another quantum state. Now, if that other state, like, if we start with like state 1 end up at state 2, if state 1 and state 2 are the same, then that quantum state is an eigenvalue of the eigenstate of the operator, or eigenvector of the operator. Now, Hermitian, hopefully we've covered plenty. Really, the other thing that we should talk about is observable or observables. And these are things that we can measure. So so for example, when I'm thinking of running a quantum computing experiment, the outcomes are all observables because I'm making measurements that I can then extract and see in lab. So that's all there is to it, pretty much. It's just like things that you can measure. And yeah, I think these were the vocab words. I mean, between like Hermitian and observable and operators were the biggest ones that we had to review. And again, just as a reminder, all quantum gates are quantum operators. But of course, there's a specific property that quantum gates seem to have, and that's that they have to be unitary. We're going to talk about it in a bit. Actually, it's a part of one of the postulates. Okay, so maybe let's move on to the other postulates then. So the fourth postulate should be very familiar by now. And it states that when we measure an observable with some operator A again, when we measure some state for that observable, the probability of obtaining a certain eigenvalue again. The eigenvalue here is AI. This is eigenvalue. Is given by the squared of the inner product of psi with the corresponding eigenstate. So maybe let's look at the analogy, and then we're going to talk about what the consequences are. So this will kind of be like saying that there's a certain probability that you will be running at a certain speed. And based on different speeds, it tells you what the probability is of you running at that speed. Again, if your coach is measuring your speed, then there's a certain probability that they would measure different values. So that's all there is to it. Now let's take our time when talking about the consequences and also doing a few examples. So really what the meaning of this fourth postulate is that it gives a probability of measuring the different outcomes of an observable measurement. So let's look at an example, right? Let's say I have, I make a sigma z, or okay, let me actually maybe rephrase that. So let's say I measure, and I start with state psi, right? And that is, I'm just going to write as generic as possible. It's alpha 0 plus beta 1. So I measure along the z-axis. Again, as a reminder, that's with the sigma z operator. So the possible outcomes are the 0 state and the 1 state, right? Because again, as we discussed earlier, those are the eigenstates of the z operator. But what are the probabilities? So I'm going to write with probability. And again, you guys, we've done this multiple times by now. This is just formalizing it in a sense. But take 30 seconds, try to do this by yourself, and then we're going to go through it. Okay, so let's get started with the 0 state. So what we said is that the probability is going to be the overlap between 0 and psi magnitude squared. And I mean, by now, it's like very obvious that that's alpha squared. And then the overlap of the 1 state, the probability of getting the state 1 is the overlap of 1 with state psi squared. And that is beta squared. Now let's spice things up, right? So we have this generic state, but now let's measure along the x-axis. So I'm going to show as sigma x, or the operator corresponding to this measurement is sigma x. So again, from previous slides, we know that the possible outcomes are either the plus state or the minus state. And so the probability of getting plus is the overlap of the plus state with psi squared. And the probability of getting a minus is the overlap of minus with state psi squared. So again, as practice, let's take 30 seconds to find out what these probabilities are for some generic state psi that we have defined up here. And then I'll go through it with you guys. And this overlap, just as a hint, will involve, probably alpha and beta because they're coefficients. Okay, so let's start doing this together. So, okay, here the first part is the plus state. And the plus state, or, it's the bra of plus, and that's 0 plus 1 divided by square root of 2. And I'm looking at the overlap of that with, actually, there is no need for fraction there. With alpha 0 plus beta 1. And since I know that the overlap of 0 with 1 or 1 with 0 is 0, I can just ignore that and kind of look at the overlap of my 0 with 0 and overlap of the 1 with 1. So when I take the overlap of the 0 here with the 0 here, I get alpha divided by square root of 2. And when I take the overlap of this one with the one state over there, I get beta divided by square root of 2 squared. So, this ends up being 1/2 the magnitude of alpha plus beta squared. Now, let's look at the other scenario. What is the probability of getting the minus state? And again, as a reminder, that's just the overlap of the minus state with state psi squared. And if I were to write this out, I'm going to have 0 minus 1. Again, these are bras divided by square root of 2. And the overlap of that with alpha 0 plus beta 1. Again, everything squared. And of course, similar to what we have above, we just need to pay attention to the overlap of the 0 with 0 and the 1 with 1, because the overlap of 0 with 1 or 1 with 0 is 0. And what I end up with here, thanks. Psi. So what I end up with here, of course, is going to be alpha divided by square root of 2. When I take the overlap of the 0 and 0 and multiply the coefficients in front. And now here I get minus beta divided by square root of 2. Because there's a minus sign in front of the 1 bra. squared. And of course, what we end up with here is 1/2 alpha minus beta squared. And now something that you can do as exercise here to kind of convince yourself that this works is, just try to add these two probabilities. And what you'll see is that they'll add up to 1. And again, just to recap, we went through a bit of math here, but the idea of the fourth postulate is that it just gives us the probability of measuring the different outcomes of an observable measurement. And what I can do, I can give you a quantum state, and I can give you for example, a qubit state, and I can give you an axis to measure it along. And using the fourth postulate, you can exactly tell me, well, using actually the previous postulates, you can tell me what are the possible outcomes. And using the fourth postulate, you can tell me, what is the probability of getting each of these outcomes. And now let's move on to fifth postulate. And again, we'll do a recap after we go through all these postulates because some of them are actually connected to one another. So the fifth postulate states that immediately after we measure, an observable A, again, same observable almost, and let me add a hat on top here, with an eigenvalue with an eigenvalue an, let's say, the state of the system is the normalized eigenstate, ket an. Again, the analogy is, this would be like saying that before your coach has measured your speed, it was not well defined. In other words, you were in a superposition of multiple different speeds. But after the measurement, the speed is well defined. And again, some of these classical analogies don't capture the full effect. And again, because a lot of these postulates that we're talking about describe the quantum world, which is not necessarily analogous to the classical world. But really, the consequence of the fifth postulate is that once we measure, the superposition state collapses to whatever state we measured. And this is something that's referred to as a collapse of the wave function sometimes. So, for example, I start with, and again, maybe let me write a note here. So this is the collapse of the wave function or the quantum state. Or quantum, let's say quantum superposition, and then I'll write wave function. So let's say we start with again a generic quantum state, a generic two-level state. Psi is equal to alpha 0 plus beta 1, and then I measure, and I get a 0 value. Then the state psi immediately collapses to the 0 state. So that's pretty much all there is to the fifth postulate. Again, it tells us, after we measure some observable and we get some, eigenvalue. Again, let's say, we measure a 0, or we measure a quantum state, and we see that that quantum state is 0. Then the state of that quantum state immediately after the measurement is the 0 state. In a way, measurement collapses superposition. You can think of it that way. And this is something that we've seen with the Schrodinger cat example, since the start of the course. The cat could be in a superposition of dead or alive until we measure the box. And as soon as we open the box and look at the state of the cat has to choose to be either dead or alive. But if we observe that the cat is alive, then the state of the cat is indeed alive and no longer in a superposition. Or, another example is the Stern-Gerlach experiment, right? So when we were sending the spin particles through, before they went through the magnet, they could be, again, in a superposition of, spin up or spin down in either direction. So maybe let me, draw this. So if we have these two magnets again, so this is magnet going over south, north, and then we have a spin that goes through. That's the superposition. So now if it goes up, we measure plus or spin up, and then if it goes down along the, again, this is along the z-axis. And then based on that, if we see that the spin has gone up, or that this quantum magnet has gone up, we conclude that it's the quantum state of the spin at this point is spin up, or 0, maybe, if we want to link it back to the to the qubit that we talked about. And the quantum state at this point would be spin down. And again, the act of kind of sending the spin through a magnet is like measuring the state, essentially. Like once we see where the position of the spin is, we'll have an idea about some observable, some it's almost an eigenvalue, and then based on that, the state of the spin will become determined. So that was the fifth postulate. Again, to reiterate, the superposition collapses after we measure the state into one of the eigenstates of the measurement that we make. And finally, the sixth postulate states that quantum states generally change, and we call the change of quantum state evolve or evolution with time. It's called time evolution again. This time evolution preserves the normalization of the state. The time evolution of a quantum system is described by some unitary operator here, u of t acting on psi of 0. Again, this operator u, of course, is a unitary, as we discussed. The analogy here, of course, is that if I went for a run and you knew where I ended up and the condition I was running in, and that can be many things, right? Like the weather, what I had for breakfast, or who I'm running with. You could figure out what my starting point was. And what that really translates to is the major consequence of the sixth postulate is that the evolution of a quantum state with time is reversible. So if something evolves forward in time, then I can also, there's an operator that I can apply to it to rewind the effects of time. So again, that is the idea of a unitary. So a unitary operator, if I say u is a unitary operator, and let's say u of t, because again, time evolution is a function of the time that passes. So in this case, u of t, it's a unitary, so times u dagger of t will be equal to, again, sneak peek yet. It will be u dagger of t times u of t, and this will be equal to the identity. So in other words, if I apply a unitary operator and then I apply the complex conjugate, or vice versa, apply the complex conjugate first and then the unitary operator, that's as if I haven't changed my quantum state at all. Now, of course, one consequence of that is that unitary operators are norm preserving. Meaning that if I have the state psi and then the state psi prime, which is equal to just u of t times psi, then the overlap of psi with psi would be the same as the overlap of psi prime with psi prime. And really what that means is that if I start with a quantum state, a valid quantum state, which this is equal to 1, the overlap of the state with itself is 1. If I evolve it with time, the overlap of the resulting state will still well, the overlap of the resulting state with itself will still be equal to 1. And of course, there's another consequence here that would be interesting. And again, this is a result of the Schrodinger equation. So the sixth postulate actually leads to the Schrodinger equation. We're not going to do the derivation because it's a little bit complicated, but just know that the Schrodinger equation can be derived from the sixth postulate of quantum mechanics. And something that's a result of that is, if I have u of t and I take the complex conjugate, which again, remember, for unitary operators, it's like reversing the effect. Then that would be the same as evolving with u of negative t. Again, meaning that, in order to reverse the effects of unitary time evolution on a quantum system, I can just run the time backwards. So if I'm if I'm going forwards in time by t, then the complex conjugate of that time evolution will be going backwards in time for time t. And of course, something that hopefully should be clear is that, if I have u of t and I multiply it by, u of minus t, that will give me the identity. I mean, of course, that's a result of what we see up here, but it's just good to have it here. And I know, Rachel has mentioned to me that you guys like real world examples. And I think I can give you a pretty good one for this last one. It's actually a project that I've been working on for the past year in lab. And what we do is that, we start with an initial quantum state in a quantum computer. The quantum computer that we're using has 9 qubits. And then we let the quantum state evolve, for some time t under some conditions. Again, conditions can be different, but in this case, it's just letting it spread throughout the quantum computer or all the qubits. And then we actually managed to rewind time using some techniques. We managed to reverse the Hamiltonian, rewind time, and see that the quantum state actually goes back to what we started with. So we move forward in time, then we do certain operations to rewind time, and then we manage to actually get back to very close to the initial quantum state that we have. So this sixth postulate is something that we are actually capable of doing in quantum mechanics and on a quantum computer. It's just a question of I guess how good your control is, but really the main message is that if time moves forward, I can also rewind the effects of time on my quantum state, and that is the notion of reversibility. It's quite fascinating. So with that, let me talk a little bit about how the postulates actually, the six postulates that we talked about, will relate to quantum computing, and then we can do again some more questions. So first of all, it gives us instructions on how to operate the quantum hardware. Because again, the quantum hardware that we use, these physical qubits are governed based on the laws of quantum mechanics, and these postulates are the underlying set of assumptions for the laws of quantum mechanics. And then it tells us, what happens after we measure our quantum circuit. So again, if you think of postulates 2 to almost 5, they're mostly focused on measurement. Again, how to link the quantum world to the classical world. And again, just to recap, so in postulate 2, we talked about how can we represent a classical observable in a quantum world, and that was with a quantum operator that happens to be, or actually rather has to be Hermitian. And in postulate 3, we talked about what are the possible outcomes that we can get after measurement, and those are the eigenstates of the operator that you're measuring. And the outcome values that you get are the eigenvalues, of course. And again, a property of these Hermitian operators is that these eigenvalues have to be real. So when I measure the state of or measure any property of a quantum system, the value that I will see is a real value, which again should make sense with the intuition that we have from the classical world. And now postulate 4 talks about what is the probability of getting different answers. And I will point out to that maybe in the next bullet point, but that's what it is. And postulate 6 tells us what happens to the quantum state after we measure it. And that is that we collapse to the state that corresponds to the eigenvalue that we measure. And finally, it allows us to calculate the probability of getting the right answer based on the set of gates that we run in our algorithm. So if you have a quantum algorithm, we're doing a set of quantum operation quantum gates, and using specifically the fourth postulate, we're able to figure out what is the probability of getting each possible answer based on the measurement that we're making. And the objective of our quantum algorithm is to make it such that the probability of getting the right answer is very high, or if not 100%. So using these postulates, we can figure out exactly what are the probabilities of getting different answers, and if the probability of getting the right answer is high enough, we call that a good algorithm, and we'll go ahead to try to execute it. Yeah. So with that, Rachel, do we have any questions that are interesting?
Could I jump in with a question, Amir?
Or Akshay, actually, sorry.
So a lot of people were very interested when you talked about in your lab how you apply the sixth postulate. So could you talk more about, you were saying like you reverse time. Is that like you're actually reversing time? Like what does that mean exactly? Like do you get younger when you work in the lab?
Well, I mean, we reverse time for a qubit, but yeah, maybe I can share some figures in a moment. I'll need 2 minutes to pull it up on my computer, but I can actually show you guys the pre-draft of the paper that we're gonna publish very soon. Yeah, are there any other questions that I should answer right now?
Let's see. So maybe a few questions from
Stop sharing my screen.
From a bit earlier on in the lecture. A few people were confused about like, what do you mean by classical information and quantum information? Like, what do those words mean?
Yeah, I mean, that's so I guess quantum information is information that is stored in your qubits, right? And I mean, they have different properties. Quantum information is strictly more powerful than classical information. Again, going into those will require a pretty decent math background that we're not assuming. But in general, you can think of classical information as information that's stored in your bits, right? So a bunch of 0, 1s and things like that. Now, quantum information is stored in a qubit, so you can store, in fact, information that is is an exact superposition between 0 and 1, or like anywhere on this thing called a block sphere, which we'll talk about later. And turns out that if you have information that can be stored as a superposition, it leads to some neat properties. And you can do some, for example, secure communication, or you can essentially it's a little bit more powerful.
Okay, then.
And I know that might not be a satisfying answer, but that is a hard question to answer without maybe going forward a few more lectures.
And then, so could you also distinguish between, so on the last postulate, you talked about the evolution or with time of a quantum state. So does that also apply to measurement? Like, can you reverse a measurement in the same way that you can reverse these operations?
That's a great question. So for all quantum operations, or rather, let's say quantum gates specifically, an assumption that we make is that, or rather, they have to be unitary, because we discuss how quantum gates need to be reversible. Otherwise, the energy noise that we get as a result of destroying information will just completely, essentially destroy our quantum computation process. But yeah, so something that happens is that all quantum operations are unitary, or all quantum gates are unitary, except for measurement. So measurement is not a unitary process. And what I mean by that is, if I measure a quantum state that's in superposition, again, let's say, that's in any superposition, and I get a 0 as a result of this measurement, no, that doesn't allow me, that single measurement, I can't actually reverse that and figure out what my exact superposition is. And since measurement is not a unitary operator, I can't actually reverse it.
So that kind of relates to what you were saying last time about when you measure, you kind of lose information.
In a sense, yes. I mean, your quantum information gets mapped to the classical world, but of course, it's not a perfect mapping.
And then I'm also wondering if you could tell us more generally about why did we spend 3 weeks doing quantum mechanics? Like, how is it going to help everyone going forward in the class?
Yeah, so everything that we will see from next lecture on in the class is going to be based on quantum mechanics. And again, just to recap what we've talked about so far in the lecture, in this 3 lecture sequence, we've talked about the 3 resources that are essential to getting any quantum speed up in quantum computing. Those are superposition, entanglement, and quantum interference. And really, with this 3rd lecture, we're kind of putting all these, not all these, but like rather the underlying set of assumptions for quantum mechanics in a framework that then we can use as a tool when we're talking about and analyzing our quantum algorithms or our quantum computers. So that's the point. Like, this is something that we're going to see all throughout our discussions when it comes to quantum computing.
Okay. And then I think one other question that people had was about so we had I think it was the 5th postulate, which was about when you make a measurement, the wave function collapses to one of the eigenstates, right?
Mm-hmm.
And then there was one postulate which was saying that when you make a measurement, you can only get one of the eigenvalues. So I forget
Right.
which one that was. So could you talk about that again? Like, when you make a measurement, do you get an eigenvalue or do you get an eigenvector? Like, what's going on there?
Right. So when we measure something, the thing that we see is a value, right? So again, in the classical world, right? Like, when I measure, let's say, the position of something, what I see is a value for a position, it's a coordinate for the position. So that is in terms of what we see as someone who's making the measurement. Now the question is, okay, after we see, that position, let's say, what happens to the quantum state? So the quantum state initially, at least what we've assumed, is that it starts from a superposition of many different possible answers, many different possible states. But as soon as we measure, a value that we see a value that corresponds to one of these states, the overall state of the system collapses from the superposition that it was in initially to that specific state, eigenstate, corresponding to the value that we measure.
I think that was all the common questions that I could find.
Okay, and I'm pulling these figures right now for you guys in the background. So again, if you bear with me for another 2 minutes, I can show you actually what the experiment looks like.
Akshay, while Amir pulls that up, do you want to provide your take on why it was so important to learn quantum mechanics for the last 3 weeks? If you have anything to add.
So actually, I noticed in one of the attendance quizzes that we had taken for labs, a lot of students had indicated that they were most excited to learn quantum mechanics this semester. So I hope that these 3 weeks have been fun for everyone. But yeah, as Amir was saying, quantum mechanics is like the foundation on which everything else that we'll talk about in the rest of the class, like that's the foundation on which it rests. And so it's really important to understand quantum mechanics if you want to understand what goes on inside a quantum computer, because what goes on inside a quantum computer follows the rules of quantum mechanics. So I think that's why it's important to spend some time on this.
Mm-hmm. And I mean, as a physicist, of course, so quantum mechanics is very fascinating in and of itself. One of the reasons why I decided to pursue physics in college, in undergrad, was because I just found quantum mechanics to be magical in a sense. And counterintuitive, which, again, in the brain of high schooler me was like magic. And something that's very neat about quantum computing, and to extend it more generally to quantum technologies, is that we take this counterintuitive nature of quantum mechanics, this non-classical behavior, and we try to solve problems or do things better than the current technology can. So I think, again, quantum computing, of course, is very cool, but it's not the end all be all for what are the applications of quantum mechanics. There's this whole emerging field now called quantum engineering, which quantum computing does fall under. And it's really a question of how can we use these counterintuitive properties that we've talked about quantum mechanics to create technology that is more advanced than what we have today.
Yeah, I can give one quick example of that from my research. So in my work, I try to apply quantum mechanics to microscopy. So the particular problem that I'm trying to look at is there a way to look at proteins and other biomolecules inside the cell at like a very, very good level of detail so that you can hopefully see all of the individual atoms in those proteins as they are inside the cell. And this would be really, really cool because you could see the proteins like moving around, folding, doing all of the things that they do. And you could see each individual atom, and that would really help with things like drug discovery, vaccine design, which is very relevant right now. And quantum mechanics really can help with this because there are ways that you can use quantum mechanics to improve how well a microscope can perform. So that's kind of where that's the application that I work on. And to do that, I need to know quantum mechanics so that I can apply it to the microscope.
And Akshay, that's specifically with quantum entanglement, right? I mean, amongst other properties, of course.
Amongst other properties, quantum entanglement bumps up like the efficiency of this. But it's actually the specific way that we want to do it. It's actually very similar to a double slit experiment, in that there is a way that you can image something without necessarily hitting it with like light or with electrons. I don't want to get too much into it because it gets very weird to think about. But yeah, it's using these weird properties of quantum mechanics to improve a real world application.
Right. Yeah, and I think that the main takeaway really from this conversation is that, again, quantum mechanics is super cool just because, it's cool to begin with, but that might be the physicist me speaking. As far as it relates to this class, quantum mechanics is the really, the gives us an extra set of tools to use for computation to solve problems that we can't using through quantum computing. But for those people who are interested, again, in technology, in developing technologies of the future, these quantum mechanical phenomena can really help us, again, advance our technology to the next level. The same way that, maybe electronics did, like when we moved from not classical, like mechanical tools to electronic tools. There's similar potential from kind of taking the next step, from electronic tools to to electronic engineering to quantum engineering tools. So again, there's a lot of potential, and there are a lot of reasons that quantum mechanics will be useful to those of you who are interested in the future. Quantum computing is a main focus of this course, but of course, and for those of you who are interested in pursuing, physics or again, technology, there's a lot to be also gained from knowing quantum mechanics.
One last thing, if I could add, Amir, real quick, is just about, I guess, more about the history of this. So quantum mechanics is present in, it's currently present in every computer, every cell phone that we have, every other piece of technology we have. Quantum mechanics is already very critical to that. We would not be able to understand how, for example, the materials inside our computer chips work if we did not have a good understanding of quantum mechanics. The way that I like to think of it sometimes is that the first part of like applying quantum mechanics was kind of like learning how to live with it. And the second part of it, which Amir and Fran and everyone is like at the forefront of, is now that we know how to live with it, how do we actually use it to directly make better and better technology?
No, that's a great point. And again, to Akshay's point, how to live with quantum mechanics, like we see the examples when it comes to Moore's law. As we're trying to make these transistors smaller and smaller, we start getting into a quantum regime where things don't behave classically and rather behave based on the laws of quantum mechanics. And of course, that is a hindrance to how small we can make our transistors before the normal classical properties that we explain are all gone. So I think again, it's a very promising field, quantum computing, quantum technologies, and again, it's something that we already are utilizing, but I feel like we will be utilizing more in the future. So Akshay, if there's anything else to add, please jump in. Otherwise, I will quickly explain, what do I mean when I say that we try to rewind time in lab, and then that could be it for the lecture if there are no more questions.
That's all for me for now.
Okay, amazing. Yeah, so this is a really cool experiment, actually, at least in my opinion, that we tried out in our lab. And basically what it involves is, it involves this 9-qubit superconducting quantum processor. We start by entangling 2 of these qubits. Like, let's say, I mean, in that case, that's just these top 2 qubits. And then we let the system kind of evolve, with time. So, all these qubits are interacting. So if I put one excitation on one, the excitation will start propagating throughout the circuit. And eventually what will happen is that kind of like this information that I had, that excitation, that like entangled state, will kind of in a sense dissolve amongst all these qubits, since they're all interacting and the excitation can jump from one to another. But now something that we can do is we can let this excitation evolve, like let this entangled state kind of evolve for some time t. Again, it spreads out among the different qubits that we have in the circuit, and then I can rewind time and retrieve the entanglement. And that is what we do. It's called, so the sequence that we use is called the Loschmidt echo, which is a technical term for just a fancy way of saying rewinding time. So what we do is that we start by entangling this qubits 7 and 4 using the sequence. And again, this should, if this doesn't make sense to you right now, don't worry about it. We're going to see this in our quantum computing lectures. This is just to give you guys a taste for what's to come. And then we let it evolve with, just let it, well, we don't do anything. We just let the interactions that we have in our quantum processor kind of, do their thing, and let this entanglement spread throughout the circuit. And then we reverse time afterwards, and we retrieve, all this information back. Now, the way that we're reversing time is that we're applying a sigma z operator to every other gate, to every other qubit, and kind of like, sandwich between this, like, again, another unitary time evolution that has the same effects. And what we managed to see is that if you look at it, this is the fidelity, like these lines that we have here, this is a dark blue one, is the overlap of the state that we retrieve. Now, again, after we move time forward and backwards with respect to the state that we started. So the idea is that how close is the state that we started with to the state that we get after we, again, move time forwards and backwards. 1 is the highest possible value, 0 is if there's no overlap. And here we can see that we can actually retrieve this quantum state with pretty high fidelity. Of course, there are sources of noise in our quantum processor, and some things that are not ideal that causes this fidelity to slowly drop. But what we see is that we can actually retrieve the quantum state pretty well. And in comparison, this is this gray line is if we don't do anything, if we don't actually retrieve time. So you would rather rewind time. We just move forward in time and nothing else happens. So if we don't rewind time, we see that this overlap drops a lot, then goes back up a little bit, then drops a lot, then goes back up a little bit, and that's because things bounce back and forth a little bit. But with rewinding time, we actually end up pretty close to that original state. And again, it's a little bit tricky, of course, in real life experiment, because there are sources of noise that there's nothing we can do about. But what this indicates, again, is that based on the laws of quantum, first of all, it indicates that the 6th postulate of quantum mechanics is correct, meaning that there is a way to rewind the flow of time, which is, again, I feel like it's very cool in a sense, and that we can successfully do that using a superconducting quantum processor. And I guess that's the main takeaway message that I wanted to give you guys from talking about the experiment, is that these things that we're talking about in the course are not just quantum theory, but rather they're there are concepts that we can see in real life and we could test. And I think that makes them even more cool. And again, that's another reason to do quantum computing. You can actually play with all these cool theoretical phenomena. But yeah, are there any other questions, Rachel or Akshay?
I think that's it. It seems like a lot of students really, really appreciated that. So thanks, Amir, for sharing. Some students were asking about Akshay's research. There's a PDF, so I'll share that in Discord after this, just so we don't have to put it it's behind a paywall if we share the link. So I'll share the PDF in Discord. But I think that's it for me. Amir, if you want to wrap us up with our last of quantum mechanics.
Yeah, sure. And again, once this paper is out, I can also share a link with you guys. Hopefully, we're planning on putting it out this coming week. So hopefully by next lecture, it'll be available to the public. But yeah, with that, this lecture wraps up the sequence of 3 lectures that we had on quantum mechanics. A lot of the phenomenon that we've talked about in the past 3 lectures will directly apply to quantum computing, and this is something that we're going to see over and over and over again once we get into quantum computing. Again, I think we had a very extensive discussion on why do we care about quantum mechanics. Quantum computing, of course, is the main focus of this course, but there are many other applications for folks who are interested either in pursuing physics or rather pursuing technology and coming up with the technology of the future. So with that, again, one point, of course, that we're trying to get across here is that although quantum mechanics is counterintuitive, there are still some set of rules that essentially tell us how things behave on the quantum level. So again, although the outcomes can be random based on some probabilities, how things evolve and how things change in quantum mechanics are not. And we can use this fact to engineer quantum computers or quantum algorithms that allow us to solve problems that we can't with classical computers. So with that, I'm very excited that now we're getting into the actual quantum computing part of the course, and hopefully you guys have all the tools that's needed to succeed in the next part. So that's about it for today's lecture. Thank you guys, and hopefully you've enjoyed the sequence that we've had on quantum mechanics.